All right. So in the last video, we looked at vectors geometrically and we moved them around in space. And that was nice, but it also got a little unwieldy in terms of how do I make sure that this thing has the same direction when I'm moving it around? Doesn't seem very like conducive to accuracy when I'm just like, oh, this looks like it's about the same. So now we're going to think about how we can think of vectors algebraically. Okay. So notice that I've got a Cartesian coordinate system up here, and I have two vectors, really the same vector repeated twice. And I want to think about how I can think of this vector in terms of its components, okay? So oftentimes when we have a vector on a Cartesian coordinate system, we call it a position vector, meaning it's giving a position in space, okay? And kind of standard position for a position vector is when it starts at 0, 0. So this particular vector, notice, starts here at 0, 0, and ends up here at 1, 2, 4, okay? So one way I can think about labeling this vector, so I'm going to call it vector U, I can label it with sort of its components. So I'm going to label this as 2, 4. Now notice I'm using these kind of arrowy bracket things. I clearly don't know the name for those. I don't know if they have a name. I'll look that up later. To indicate that this is a vector quantity. Okay, so U broken down into its components is going to be 2 and 4. Now I keep using that word components. I'm going to come back to that in a little while and explain that a little bit further. Okay, but notice down here, this vector is the same as this vector. How do I know? Well, it's the same magnitude, the same length, and the same direction. That means those two vectors are equal, but it's got a different position on our Cartesian coordinate system. However, I can still think of this vector in terms of its components, 2, 4. And let's sort of look at that by looking at where this vector starts and where this vector ends. So the initial point of this vector here is at 1, 2, 3, 4, 5, negative 5, 1, 2, 3, negative 4. Okay. So the initial point is here at negative 5, negative 4. The ending point of this vector is right here at negative 3, 0. Okay. Now, I want to talk a little bit about how we can think about the length of these two vectors. Okay. Well, notice that if I think of this as a starting point and an ending point, then I've got 2 points. The point 0, 0 that defines the starting point of the vector and the point 2, 4 that defines the end point. Don't we know how to find the distance between 2 points? We used this a lot in our earlier trig sections when we were finding the radius and calculating trig functions using the x, y, r definitions. Now, the other way to think about this is Pythagorean theorem, right? Distance formula. So the distance between 2 points, we'll call them x1, y1, and x2, y2. This really comes from the Pythagorean theorem, right? If I've got 2 general points, x2, y2, sorry, x1, y1, really doesn't matter, x2, y2. The distance between them can be given by the Pythagorean theorem. A squared plus b squared equals c squared. C squared is the distance between them. This is the difference in their horizontal coordinates, or x2 minus x1. This is the distance in their vertical coordinates, or y2 minus y1. So this distance is going to be the square root of x2 minus x1 squared plus y2 minus y1 squared, which is our distance formula. The square root of x2 minus x1 squared minus y2 minus y1 squared. Okay. Now, if we apply that distance formula to these 2 vectors here, we should, in theory, get the same thing. So let's check that. So using this guy, I've got 2 points, 2, 4, and 0, 0. The distance between those will be 2 minus 0 squared plus 4 minus 0 squared. 2 minus 0 is 2. 2 squared is 4. 4 minus 0 is 4. 4 squared is 16. 4 plus 16 is 20. So the distance between these is the square root of 20. If I simplify that, 20 is 4 times 5, square root of 4, square root of 5. I get 2 square root of 5. So the distance from here to here, also known as the magnitude or length of this vector, is 2 square root of 5. Now if I look at this vector here, which starts at negative 5, negative 4, and goes to negative 3, 0, and I again apply the distance formula. Distance formula says negative 3 minus negative 5 squared, excuse me, plus 0 minus negative 4 squared. Negative 3 minus negative 5 is negative 3 plus 5. Negative 3 plus 5 is 2. 2 squared is 4. 0 minus negative 4 is 4. 4 squared is 16. Now look at that. We get the square root of 20, which we saw before was 2 square root of 5. So these two vectors have the same magnitude, which we knew they needed to, because we knew that for two vectors to be equal, they have to have the same magnitude or length and the same direction. Okay? So, excuse me, my goodness. Remember that we write the magnitude of a vector. Magnitude, I can't spell. Using kind of the bars. So the magnitude of u is equal to 2 square root of 5, or the length of this vector, which we found just by using our regular length formula or our distance formula. Okay. Now, the magnitude of the vector does not change depending on where it is in space. Okay. All right. So we know that these two vectors are equal. We know that we can think about where they are based on their starting point and their ending point. Okay. So the other thing that I've kind of glossed over is I keep calling these things the components of the vector. Well, where do those things come from? We often think of this first component as the horizontal component of the vector. Why? Well, because it tells us how far we move horizontally to go from our starting point to our ending point. So this vector, I'd have to move 2 points horizontally to go from here to here. That makes this the vertical component of our vector. And the vertical component tells me how I move vertically to go from the starting point of my vector to the ending point. 1, 2, 3, 4. Okay. Notice that that does not change even when my vector is down here. If I start here, to get to this point, I'm going to have to move horizontally, 1, 2, and vertically, 1, 2, 3, 4. Okay? So that's why we can think of our vector as being defined by these components, no matter where it is on our Cartesian coordinate system. Okay? Turns out that defining a vector this way by its horizontal and vertical components also is going to make it really handy to do things like add the vectors, subtract vectors, and scalar multiply the vectors. All right, so we know that this vector u has components 2, 4. We also saw that vector u had magnitude 2 square root of 20, square root of 20, which reduces to 2 square root of 5. Okay, so I put another vector up here. We're going to call this vector v. Okay, and what I want to think about is how we can figure out the components of v. Okay? Remember, the components tell us how we move from the starting point of the vector, which in this case is at 0, 0, to the ending point, which in this case is at -1, -3. Okay. Well, to go from here horizontally, I would have to go left 1, which tells me -1. Negative indicates moving to the left. Then I'd have to go down 1, 2, 3. Down 3 would be -3. So vector v has components -1, -3. We can then calculate the magnitude of v using our distance formula. Okay. Notice the distance formula, when we start at 0, right, or when we have our components, reduces to just doing the square root of your horizontal component squared plus the square root, not the square root, all of this is under the square root. The square root of the horizontal component squared plus the vertical component squared. So in this case, excuse me, I have 1 squared, which is 1, plus, sorry, -1 squared, which is 1, plus -3 squared, which is 9. 1 plus 9 is the square root of 10. So the magnitude of v is the square root of 10. Now I want to think about adding u plus v. Okay? So if I want to think about adding u plus v, well, geometrically, remember that this means I'm going to add these vectors tip to tail. Okay? So if I take u and put it back up here, well, there's my u, 2, 4. Okay? Then when I add my vector v, okay, it's going to look something like this. Woo, losing my stickiness here. Let me fix that real quick. All right, now this guy's sticking a little bit better. Okay, so adding tip to tail. So u plus v. The result, remember, goes from the initial position of u to the ending position of v. Okay. Now, this is clearly not perfect because I'm doing this with little sticky things and I hand drew my Cartesian coordinate system. But it almost looks like the result right here ends at 1, 1. Or in other words, this purple vector will be the components 1, 1, over 1 and up 1. Does that make sense? Well, the nice thing about having vectors expressed component-wise is if I want to add u plus v, well, that means I'm adding component 2, 4, that's the component version of u, plus -1, -3. But if I think about horizontal and vertical components, well, if I go over 2 and then back 1, over 2 and then back 1, right, is going to get me to 1. In other words, 2 plus -1 gives me 1. My vertical components tell me I go up 4, 1, 2, 3, 4, and then I have to come back down 3, 1, 2, 3. 4 plus -3 is 1. What does this really say? This says when we add vectors, we can add component-wise. Okay? In other words, u plus v is going to be 2 plus -1. That'll give me my horizontal component. And then 4 plus -3. That'll give me my vertical component. All right, let's do another example of this. So I'm going to get rid of this mess. Because, man, I got a little messy, even for me. And let's say that I have two vectors defined component-wise. So let's now say that u is equal to 1, -4, and v is equal to -2, 3. Now, if I want to add u plus v, this means I can add the horizontal components, 1 plus -2, which is -1, and then add the vertical components, -4 plus 3, which is also -1. Now, let's see if we can sketch a picture to show why this is. Okay, so if we're doing u plus v, that means we're starting with u. Well, u is the vector 1, -4. So the vector that if it started here, we go over 1 and down 1, 2, 3, 4. So this would be vector u. Okay. Now we're going to attach to that vector v. When we add vectors, we add tip to tail. So the tail of vector v is going to start right here. But one way to think about the components is as directions. This tells me that from my initial point of v, I go left 2, 1, 2, and then I go up 3, 1, 2, 3. So there's my vector v. I'm adding u plus v, tip to tail, and the resultant vector, meaning the solution to u plus v, would start here and go to v. And notice that's exactly the vector with components -1, -1. So when we add vectors algebraically, we can really add components. Okay? Similarly, if I subtract vectors, so let's say I wanted to do u minus v here. Well, remember that u minus v I can think of as u plus a -v. But if my original v, this guy here, was -2, 3, that means if I were to sketch v starting in standard position, I go down 2 and over 3. Wow, no, I wouldn't. Ooh. Horizontal, then vertical. Okay, that means I go left 2 and then up 3. Right? So I could think of v as starting here at 0, 0, and going to -2, 3. But remember, a negative vector would just have the exact same length, but go backwards. Okay, so the negative of v would start here at -2, 3, and go to 0, 0. Okay? components of that look like? Well, I start here and I have to go 1, 2 units over, so 2 units to the right, and then I'd have to go down 1, 2, 3 units. Down 3, that should be negative, right? So if v is -2, 3, negative v would be 2, -3. In other words, we just multiply the components by a negative, okay? That means that I can think of u plus -v, all of my markers are on their lips, as 1, -4, plus our negative v is 2, -3. So that'll give us 1 plus 2, which is 3, 2 to 4 minus 2 to 4 plus -3, which is -7. So I expect u minus v to go to 3, -7. If we look at this graphically, it's going to get messy, I'm sorry. Here's our u. We want to do plus -v. Negative v is 2, -3. So that means here I'm going to go over 2, 1, 2, and then down 3, 1, 2, 3. So I'm going to be ending here. So there's -v. So my resultant would go from here to here. And notice, this is the point, 1, 2, 3, 1, 2, 3, 4, 5, 6, 7. 3, -7, which means this vector is 3, -7 component-wise. Okay? Oh, all right. It's getting a little bit messy. It's getting a little bit late. I think I'm starting to not make as much sense. So the very last thing I want to do, thinking about these guys geometrically, is I want to think about scaling. So remember when we scaled geometrically, right? I just made kind of carbon copies of my vectors. So if this was my vector A, this would represent 2 times A. In other words, same direction, twice the magnitude. Okay? Well, if we're thinking of this algebraically, I'm thinking of breaking these into component parts. Goodness. Okay, so let's start out with a nice easy vector. We'll start it here and we'll say that it goes over to, let's just do this. So my vector starts at 0, 0 and goes to -2, 1. Okay? So that means we'll call this vector u. The components of vector u, my horizontal component is -2. My vertical component is 1. So I can think of this as the vector -2, 1. Okay? Now what if I want to multiply this by a scalar or scale this up? So let's say I wanted to do 2 times u. Well, geometrically speaking, or visually speaking, that means I'm going to double the length of this vector. What is this new vector that we've created? Well, it starts at 0, 0, and it goes to 1, 2, 3, 4. It goes to the point 4, 1, 2, 2. Sorry, -4, 2. So component-wise, this vector would be -4, 2. See any relation to where we started? When we're multiplying by a scalar, I can multiply each component by that scalar. So 2 times -2 and 2 times 1, which gives me 2 times -2 is -4, 2 times 1 is 2, okay? Which gives me that new vector, -4, 2. So multiplying by a scalar, I'm going to multiply each component. All right, so say I have 2 vectors defined by their horizontal and vertical components. I want to perform all of these operations. A plus B, B minus A, 3 times A, 1, 6B, and 3A plus 1, 6B. Okay? Well, to start with, if I want to do A plus B, right, I'm just going to add the components of A plus the components of B. So -3, 4, plus 2, 3. -3 plus 2 is -1. 4 plus 3 is 7. So A plus B is going to be 1, 7. Now if I want to do B minus A, technically that'll be B, which is 2, 3, or plus -A. But to get -A, I just multiply A through by -1. Negative times -3 would be +3. 4 times -1 would be -4. And then I'm going to add 2 plus 3 is 5. 3 plus -4 is negative 1. So b minus a would be the vector 5, negative 1. All right, now to do 3 times a. 3 times a means I'm going to take 3 times a, negative 3, 4. But remember, scalar multiplication, I can kind of distribute or multiply each component by our scalar. 3 times negative 3 is negative 9. 3 times 4 is 12. Now if I want to do 1/6 b, that's 1/6 times 2, 3. 1/6 times 2 is 2/6, which is 1/3. 1/6 times 3 is 3/6, which is 1/2. Okay. Now last, we want to do 3a plus 1/6 b. Well, luckily, we've already computed 3a. 3a is negative 9, 12. We're going to add that to 1/6 b, which we've also computed, 1/3, 1/2. Adding these together, negative 9 plus 1/3, so I'm adding component-wise. Negative 9 plus 1/3, well, that'll be 8, negative 8 and 2/3. 12 plus 1/2, well, that'll be 12 and a half. Okay, all right, so adding things component-wise, when we have our components in nice horizontal and vertical. Next, we're gonna kind of take a look at what does this look like if we define our vector not as kind of a vertical and horizontal component, but rather as a distance, this distance, and an angle, theta. This is gonna bring us back to where we've been trig-wise.